So I want to introduce Mark Hoefer. Mark did his undergrad at UCLA and a master's degree at Harvard, and then got his PhD at University of Colorado at Boulder, working with Mark Oblowitz. He then went on to a postdoc at NIST and then Columbia before joining the faculty at North Carolina State University, where he was for about 5 years. But then he rejoined CU Boulder in 2014, where he's been ever since. So now Mark is the department chair at the Applied Math Department at CU Boulder after the tragic and unexpected passing of our friend and colleague Keith Julian. But I think that he's still keeping the department going very well, even as best as we can, I guess. Mark is an expert in nonlinear wave dynamics, combining many different methods from asymptotics, numerical calculations, and also laboratory experiments. And his work has been acknowledged with a career award and a T. Brooke Benjamin Prize in Nonlinear Waves from SIAM in 2020. And then today he's going to tell us about waves of waves. So take it away. You have maybe tried to wrap up at around 12:10 or so. Okay. Time for more questions.
Thanks so much, Daniel. Thank you, everybody, for coming. I'm excited to be here. I've never visited Northwestern. Unfortunately, I have this showing up, so there's the trade-off, I guess, that we get a little fun bar at the bottom here. I don't know how to get rid of. Oh no, that's yours.
Okay,
that's on
I can fix that.
Right. Sorry, because I didn't recognize the dog. The dog on the computer. So. You know, I love dogs. I have a dog. Okay. Okay, thanks. So I first want to kick off by acknowledging a relatively new journal that was just inaugurated or opened in last fall, the Journal of Nonlinear Waves, published by Cambridge University Press. And I just want to, I start all my talks with this to announce it. We're really excited about this new journal, and it's nonlinear waves broadly interpreted. So anybody, and I know a lot of folks here are doing, waves and nonlinear wave phenomena. So we really invite you to submit your latest great work there. Before I start, I want to mention a few collaborators that bubble up during my talk here, and in particular, a longtime colleague and collaborator, Gennady L. In the UK at Northumbria University in Newcastle. He and I have been working many years on developing what I'll talk about today and applying it in a lot of different contexts. And I think you also, some of you met a former PhD student, Yifeng Mao. She came and gave a talk here not too long ago. And these other folks are people I'm really grateful to be working with. So let me jump in. So I'm going to do this. It's kind of more of a pedagogical talk. We're going to work our way up through things. And thanks. And so I want to start with just linear waves, okay? And so let me just take this very idealized, simplistic model of first order in time and nth order in space, okay? And I'm interested in the initial value problem for decaying data. Okay, so you can solve this. In PD class, you would see you just use Fourier transforms, and what you get is a superposition of traveling trigonometric waves, okay? But the key object of interest here that really characterizes the waves is the dispersion relation. And so given here, it's a polynomial for this model. And under the assumption of a real dispersion, so real frequencies only for all real k, and that the second derivative, a non-zero curvature for the dispersion, then there's interesting wave dynamics that you can describe using the WKB approximation. Okay, so you have a rapidly varying wave. I'm just putting a cosine here, and I have a slowly varying envelope. And if you go through the multi-scale analysis, you end up with these two equations here. And I'm going to re-express them in this way. And here's kind of the OG simplest wave theory of waves. Because why? Because we end up, at least for this equation here, we call it the conservation of waves. It describes slow evolution of the wave number of the waves. And in particular, we're trading a linear dispersive wave equation for a nonlinear wave equation. It is a quasi-linear equation, and it's degenerate. So this system, so notice the amplitude is decoupled and it is linear because the original equation was linear. And the characteristic velocity, okay, so for this quasi-linear system is degenerate. Okay, it's a double characteristic. And this is known as the group velocity. Okay, and you can understand that by looking at, say, a wave packet. So you have a rapidly varying wave with a slowly varying envelope, and the motion of that envelope is given by the group velocity, but you saw it was quite different from the phase velocity of the underlying carrier wave. And here's a nice little example of using that conservation of waves equation. You can generalize it to multiple dimensions. And I like this picture, I think you can see it here, of Rottnest Island off the coast of Australia, where you have waves propagating in this direction, and you can see that they're being refracted, okay, by the island. And this has to do with variable water depth. Okay, so the direction of wave propagation is influenced by the medium in which they're propagating. And here is some further modeling of ray tracing. Okay, so this is where now we put in, say, a single wave of a certain frequency, and we look at its trajectories, okay, as it moves through this medium. And you can see that there's refraction, there's constructive and destructive interference that can occur depending on the underlying. This has a current that's driving the system. So this is just kind of a nice little application of wave theory of waves. Yeah.
So one of the assumptions you made was that the dispersion relation, there was like a polynomial expansion. How restrictive is that approximation?
We could generalize to quite a large class of frequency wave number relationships. So I did a polynomial, but you could do an infinite series. You could even do a pseudo differential operator. So you have just a Fourier multiplier, essentially. So this whole approach works generically. And the key thing is that you need real frequencies and a non-zero curvature to get interesting dynamics. Yeah. Okay. So let me take that simple linear theory and apply it to a problem that I'm going to revisit again. So this is the wave maker problem. You have a lot of situations in which you have a source or you have a boundary in which you either want to or you observe the generation of waves. And here's a few examples. And we can model that with our wave theory of waves by taking this equation and now giving what we call a signaling problem. Okay, so we have no frequency initially, there's no waves, and then suddenly we turn on some non-zero frequency at a boundary. Okay, so this is only for x positive. And we can find a solution to this problem, an exact solution, so long as the group velocity is positive. Okay, but here's the challenge. This dispersion relation is inverted. Right? We had omega of k, it was polynomial. We have to invert that. There's multiple branches. Which branch do you select? Okay, and it turns out, at least for many problems of interest, that the only requirement is that the group velocity be positive and that your wave number be real. Okay, I'll show you what happens when the wave number is not real, because that can happen too. But you get this nice modulation solution. And furthermore, you can identify what's known as a critical frequency. So whenever the group velocity is zero, then there's going to be some bifurcation in the dynamics you would expect. Okay, and I'll show you what happens in such a scenario. And for that, I want to refer to an experimental platform that I'll bring up several times here, and it's known as it's a core annular flow. Okay, so we have a column filled with glycerin, so a very viscous Stokes fluid, and then we inject from below a lighter but still viscous, but much less viscous. So the ratio here is a small parameter, Stokes fluid inside. And if you just inject at a constant rate, you establish a kind of fluid-filled pipe. It just pools up at the top and you suck it out. Okay, so that's the system. And conservation of mass, we have very negligible diffusion across the interface. And so you can generate waves at that interface. And so this will be our wave medium of interest. And you can control the boundary. Okay, so it's an initial boundary value problem. And we can get a nice long wavelength model. Okay, A is the non-dimensionalized cross-sectional area, and Z is going to be the vertical distance, and T is time. What you'll notice about this model is that these third order terms here are nonlinear. Okay, and that's because we've made no assumption on amplitude here. So we can get very large amplitude waves that obey this equation. If you look at linear waves, this is the dispersion. So back to your question, here's an example where we have rational dispersion. Okay, and this was originally studied in the context of magma dynamics, but we now use it as a platform to study nonlinear wave and linear wave phenomena. So here's the linear problem. We just want to generate waves at the boundary and see if they propagate or not. And here's a space-time plot. I'll show you more of these in the future. And what you can see is that there's no waves in this region, and then pretty soon we establish a nice propagating wave. And here's the development of that wave, and you can kind of see a front that is moving to the right, okay? And we can therefore measure a group velocity. We can measure the speed of that invasion into the quiescent regime. And some manipulation of that dispersion relation I showed you relates the group velocity to the frequency, okay? For the branch in which you have positive dispersion. There's two branches here, and this black curve represents that branch, and these are our measurements, so it does a pretty good job, okay? But the maximum frequency, this is the critical frequency. This is non-dimensional. I've non-dimensionalized things. So 1/2 is our critical frequency. And if we go above it, we do see indeed a bifurcation. So below that frequency, we get propagating waves, okay? And above it, we see decay. And you actually see exponential decay. This is along a certain space-time curve through that contour plot. And we're plotting some additional details here I didn't describe, but is in this paper. And the purpose of this work was to prove that that radiation condition works. Namely that to select the appropriate wave number, given a certain frequency at the boundary for the wave maker, we need either positive group velocity in real wave number, or the imaginary part of the wave number is positive. That is spatial decay. And here we see that dichotomy realized. Okay, so that's the linear theory. Let's upgrade a little. Okay. So to upgrade, I want to upgrade by adding nonlinearity. So I'm going to add an amplitude dependence now to my dispersion, my frequency. Okay. And this is a nonlinear frequency shift that's commonly seen in wave problems. And it turns out that that system I showed you before, this term only matters, at least to the order of interest, to be added here. Okay? But now it's fully coupled, right? And this splits the group velocity. Okay? You get a splitting of the group velocity. If you look at the characteristic velocities now of this quasi-linear system, so the eigenvalues of this matrix, you can see the group velocity and then an amplitude-dependent term. Okay? And, well, we have a square root. So we're immediately thinking, well, these are characteristic velocities, so it matters if they're real. So strictly hyperbolic, if and only if this is a positive quantity. Okay. Now, This is a 2x2 quasi-linear system that can be diagonalized, and in terms of Riemann invariance. So we have the amplitude here, and then we have this integral you can do for your given physical system, an integral over K. Okay, and this Riemann invariant structure turns out to be important for some further things I'll talk about. Okay, and you can upgrade this further by allowing for what's known as an induced mean. And all it does is it changes this omega 2. Okay, so you get an omega 2 tilde. Okay, let's do a quick application of this theory. So I mentioned that these need to be real for hyperbolicity. What happens when they're not? Right? So if we get a complex characteristic velocity, then the system becomes elliptic. And the initial value problem is ill-posed, right? It's unstable to long wavelength modulations. And it turned out that this was a big deal back in the 60s. This is the first time it was observed. And here's a big gravity waves, okay, in a wave tank. And you can see that they look very nice and uniform on the left, and on the right, they've broken up, disintegrated somehow. There's some instability happening, and it turns out that it's due to this, we call it modulational instability, okay? And basically, omega 2 is going to change sign when KH is this magical value for water waves. Yeah.
So to me, the second image, it looks like you have structure kind of
Transverse.
Transverse. Whereas what you're describing here, if I understand, is like a 1D picture.
That's right.
So
that's right. So in this context, you can actually prove that in deep water that there is also a transverse instability, but depending on the system, and they were able to describe it with this kind of one-dimensional instability of Stokes waves. Yeah, yeah. But
those
you're right.
instabilities kicking at the same time, like the same.
No, not necessarily.
Okay.
This is finite depth, and we're in this regime. We're in very deep water, so this parameter is a bit bigger than here. So it's the transverse instability and the modulational instability are always there. Okay, so let's now apply this to this wave maker problem in the regime of stable. So we have real characteristic velocities. I give a signaling problem. There's now two equations. I have to give an amplitude and a frequency at the boundary, and I look at what happens. Okay. For this problem to be well posed, not only do I need real characteristic velocities, but I need both characteristic speeds to be positive. I'm giving two pieces of information at the boundary. They both need to propagate into the domain. And so I have this requirement that V minus, the smallest characteristic speed, must be positive, evaluated on the boundary. Okay. It's called a time-like boundary. And we can identify a critical speed, a critical frequency. When V minus is 0, we can work out what the critical frequency is, and you'll see that it's different from what we got from the linear theory, right? So now we have an amplitude-dependent critical frequency that can go either way. Okay, so the sign SIGN of this could be positive or negative, so we could either have the critical frequency up or down. Okay, and the same condition holds. So if my input frequency is below this critical frequency, then I'm going to get propagating waves. Above it, that's a question mark. Okay, and I'll save that for another day. But that is an interesting, actually open question for the nonlinear problem. So that was a long warm up to other things I want to go into now and generalize all this. That was linear and weakly nonlinear. So how am I going to generalize? I want to go to strongly nonlinear. Okay, so now we're going to have solitons, solitary waves, nonlinear periodic traveling waves, and I'll describe for you Whitham modulation theory and some applications, just a taste of some fun applications that we can do. So this is a colloquium talk. Let me just start by introducing solitons. Perhaps many of you have heard of them, but a Scottish engineer, John Scott Russell, he happened along a boat suddenly stopping at the head of a channel, and a heap of water propagated for very long distance. He followed it on horseback, and he called it the Great Wave of Translation. And he went into a lab, and here's some of his lab measurements of such a great wave. And it took a little while for people to find a simple mathematical model and solution to describe this wave. And it was left to Boussinesq and Korteweg and de Vries to finally do that. And so here's what we now call the KdV equation. And if we look for traveling waves, we can integrate once, get this nonlinear ODE, and here's the phase portrait, okay? And the red one is homoclinic orbit. There's a saddle there. And this homoclinic orbit is the soliton, or solitary wave, okay? So how did the term solitons come about? So Zavodsky and Kruskal, back in the days when computers were still a novelty, they decided to simulate this equation, but they made it a little bit more complicated by adding a small parameter here, okay? Or a parameter, let's say. They gave periodic boundary conditions and cosine initial conditions. And this is the value of epsilon they used. So I'm going to run it. This is what they observed in the numerics. And you saw that there was a smooth breaking up into a bunch of pulses. And these pulses appear to remain. Okay. And if you let it run long enough, they mix and lots of things happen. Interesting dynamics. But the robustness of these pulses led them to call them solitons. Okay. Kind of particle-like waves. Where does that particality come from? It turns out it's the structure of the equation itself, okay? Remarkably, it was discovered just 2 years later that the KdV equation, okay, I've rescaled it with a 6 here, is equivalent to the compatibility of these two linear problems. Okay, let's look at this a little more carefully. So this is the Schrodinger operator. Okay, U is a potential, and lambda is a spectral parameter. Okay, so you first characterize this spectral problem, and then you evolve the eigenfunctions in time according to this equation. We need continuity of the mixed partials. That is true if and only if KdV is satisfied, and we assume that the spectrum does not change. Okay, that is in essence what we mean by integrability in the sense of inverse scattering theory, okay? And a result of this that was discovered here is you can get special solutions. In particular, you can get n-soliton solutions. And the first one is the famous Sesh squared. Lambda 1 is the amplitude parameter. But you can get any number of kind of interacting solitons, and here's the second one, written in a certain way. And it's important for me to mention this, the spectrum that's associated, say, with this solution. Suppose I take U to be this, put it in here, and I try to compute the spectrum. What you'll find is a semi-infinite band, and that's kind of the generalized Fourier modes, okay? And you'll have an eigenvalue, a single eigenvalue. And because that eigenvalue is unchanged, that's the real origin of the soliton, stable structure. And if we had two, that would be this solution, and so on. Okay. So let's observe some solitons in experiment. So here's our conduit. We have a smaller one moving slower than a bigger one faster from behind, and they interact. And here's my space-time diagram, and you can see the interaction. What's the result of interaction? If you look carefully, what happens is that this faster guy gets advanced, okay? And that advancement is what we call the phase shift. But if you look at the slope and the amplitude, before and after interaction, they're basically the same, at least to within percent or so for this experiment, okay? And so this is a nice example. So what is the property of solitons? Not only that we have traveling waves, but when they interact, they impart just a phase shift. They otherwise do not change their properties. Now you could dive down deeper a little further to understand the interaction. And Peter Lax did this in this monumental paper from 68. First, he introduced this notion of what's known as a Lax pair. It's a generalization of that compatibility argument to operators, okay? And that serves as the basis for a lot of what people define as integrable systems. If you can find a Lax pair for a PDE, you call it integrable, okay? But in section 2, he also characterized the two-soliton solution and its interaction. And let me explain it to you from an experiment, okay? So on the left, I'm showing 3 different geometries of interaction. And on the right, I'm showing in red just before they interact or right when they're about to. Blue is the peak of interaction and black is just after. So you can see the 3 different scenarios here. And the first and last are the simplest, easiest to explain. Bimodal just means we have 2 local maxima for all time throughout the interaction. Unimodal, it's 2 local maxima except at the peak of interaction, right? And then mixed is where you kind of have a mixture of both. So here it becomes unimodal. This is actually a shoulder. Here it's not an extremum anymore, flexion point, and it becomes bimodal again in the interaction. So this is a kind of continuous deformation as you vary parameters across. And what you'll notice is that in all of these interactions, the amplitude goes down. So it is absolutely not superposition. There's no linear superposition. Okay, so it's a truly nonlinear process. Okay, let me also talk now about the canonical wave for KdV. So if we now go inside the homoclinic orbit, we have these periodic orbits here, and they can be written down in terms of special function known as the Jacobi CN function. It generalizes both cosine and the hyperbolic secants, okay? And it depends on this parameter m. So when m goes to 0, we recover the linear waves. And when m goes to 1, we recover the soliton. So that's basically moving you inside this homoclinic orbit here in the phase point. And there's some examples. The spectrum, remember I showed you the spectral problem for the Schrodinger operator. You still have a semi-infinite band, but now you have a finite band, okay? And there's a gap. And these edges of the band edges turn out to parameterize the periodic traveling wave. And it will be convenient to use that parameterization, as I'll show in a second. Let's see here. So we have now periodic traveling waves, and we need to modulate them in space and time because they're spatially extended. So we need to have some description, and that'll be the Whitham modulation theory I'll get to in a second. But I do just want to show you that KdV is an idealized example. And you may ask, oh, is that too simple? It's integrable. Well, here's the conduit equation, and it has essentially the same structure. We have a homoclinic orbit for the solitary wave, and we have periodic orbits inside. Okay, and so you can see that here, and we actually can observe these. So here's I call it a canonical-like wave, and that's going to be in blue. And then the dashed black is the actual periodic traveling wave solution from that phase portrait, okay? And just to show you that it really is strongly nonlinear, we just used, for example, the linear approximation in green. It's horrible. The 2-mode approximation, the first 2 harmonics, it's also horrible. But when you compare, this is an averaged profile. We took many oscillations and we averaged them. And you can see that the profile agrees very well with the profile of the solution. Furthermore, we can plot the dispersion relation. We're doing a wave maker. We're putting in a frequency and an amplitude and a profile at the boundary, and we launch a wave, and then we measure its wave number. And sure enough, we can get a reasonable agreement with theory, okay? These are each trial. So the horizontal axis is just each independent measurement, okay? And we're just comparing what was predicted from what was observed. Okay, so let's get to the full W-toe here. Okay. Now for this, before we had linear theory, we had just one modulation parameter, K. Then we added an amplitude. Now we're going to add a mean. Okay, we're going to add a mean. So now it's this is kind of a KdV-like or similar to that conduit equation scenario in which we have periodic traveling waves with three parameters. Okay, and these are the physical characterization. And it turns out that the innovation was to figure out how do we get these modulation equations? How do we just kind of have waves describing modulating waves? And this is the system. Okay, this is known as the Whitham modulation equations. And a real quick check you can do is you take your matrix and you look at its eigenvalues, and that can say something about stability of the wave. Right? If these are real, then it's modulationally stable. So hyperbolic. And let me just quickly run through KdV just to show you what it's like. So we have this equation. We have our canonical wave solution. It's a traveling wave with some parameters. And what parameters? Well, there's different parameterizations. If you just jump in and start, you can integrate this twice, and you get a nice oscillator ODE equation. And it's cubic. It has three roots. So we can use the three roots as the parameterization. It's a convenient mathematical parameterization. Okay? And the idea then is to average the conservation laws associated with this PDE. Okay? KdV is an integrable system, has an infinite number of conservation laws. Here's the first two. This is a conservation of mass. This is a conservation of momentum equation. And we need a third equation, and that's going to be a kind of consistency or compatibility of the phase, which we call conservation of waves. And so what is this? This is just projecting the PDE dynamics onto the manifold of periodic traveling waves. Okay, it's finite dimensional, but it is PDE, right? These are now varying in space and time. Other ways you can derive this, these equations, you could use multi-scale methods, multiple scales. Whitham himself really championed average Lagrangian approach, so he uses average variational principle. So what you do is you stick in the periodic traveling wave, you integrate over the fast phase, and then you apply a variational principle to that. Okay? And that'll give you Hamiltonian structure and so on. Turns out you get the same modulation equation, no matter which way you go. And so what have we done? We've effectively traded a nonlinear dispersive wave equation for the waves for a first order system of quasi-linear PDE that describe the modulations of those waves with waves. Okay. All right. So one other comment that is worth giving on parameterization. So Whitham discovered, and it's quite remarkable that he discovered this, because this is a highly non-trivial fact. When you have a 3x3 quasi-linear system, it's very special when you can diagonalize it. And it turns out that this system is very special. Okay, it comes from KdV. It's not surprising. It's an integrable system. This special linear combination here turns out to be a nice representation that allows you to diagonalize the modulation system. Okay. And furthermore, if you go back to the spectral picture that I showed you earlier, the R's are just the band edges. And so now what we're saying is a wave theory of waves says modulate the spectrum, okay, in space and time and see what happens. Okay. And there's all kinds of interesting things you can do. For example, take R2 to go to R3, and now you get an eigenvalue. That's the soliton limit. Take R2 to R1, you're going to linear waves. You get your semi-infinite band. Okay. But this was all very formal. Lax and Livermore and Benekides, you can actually solve this equation exactly, okay, using inverse scattering theory. And the question they posed, the natural question in this context, if I have my small parameter here and I want to solve the initial value problem, does that limit exist? Does that limit exist? And it turns out it does, but it's a weak limit. Okay, weak limit. And you'll see why that makes a lot of sense, but weak limit, you're testing against test functions. You're taking in a product of your sequence with test functions, that's averaging, right? And that's exactly what Whitham modulation theory describes. So now let me give one very important application of Whitham modulation theory, and it's the DSWs. And I want to go back to the Zabusky-Kruskal experiment here, but I'm going to make epsilon smaller. So let's look at the simulations when epsilon's smaller. Okay. Okay. So what you see happening is that these pulses are getting narrower as I decrease epsilon. They're actually, width is proportional to epsilon. You can just see that by scaling. And so what's happening is that we're generating more and more oscillations. So considering them in an average sense starts to make makes more sense. Okay. And there's a lot of interesting features in that solution, but let me tell you a little bit about the history. Okay, so dispersive shock wave, or DSW. So the first lab experiments, they're shown here, and they were in a water tank, very long, shallow water tank. And these are measurements at different positions in time down the tank. And you can see the nice development of oscillations here at the leading edge. This is kind of like a step or Riemann problem, I'll show shortly. But people tried to explain this using, let's say, more familiar methods. Namely, they would take the KdV equation and they would add dissipation. Okay. And here's what the phase portrait looks like for that KdV Burger's equation. Okay. No longer do we have homoclinic solutions, but we do have heteroclinic solutions. We have a saddle and a spiral here. And so you can see that that's there, but it fails to capture DSWs who are unsteady. So let's see the difference. So let's take this equation, give this smooth initial condition, monotonic, let it run, and at a specific time, plot it. That's what I'm doing. So the black is where I set dispersion to 0, epsilon 0, and I just get Burger's equation. I get a shock front, classical shock, viscous shock. When I turn on the dispersion and I have a certain ratio, now I start to see oscillations, but it's still a traveling wave. Okay, it asymptotes very quickly to this traveling wave that just translates. But if I turn off dissipation completely, or I look at timescales where it's negligible, I start to see the development of this unsteady structure here. You can see that, for example, the front is moving faster than in the dissipative case. Okay, so there's a fundamental distinction here, and this can be observed in our lab. So we have a conduit here that's thinner than here, so we just gradually increase the flow rate, and what happens is, boom, you emerge all these oscillations, and it just keeps growing and growing. Okay, and here you see it in the space-time plot. And this is the unsteady dispersive shock wave, DSW. Okay, and there's a number of properties of this that I want to call out. In particular, we have a front and a back, right? We can see that here. Go back here. And it turns out that this guy behaves like a solitary wave or a soliton. And its speed is equal to the solitary wave amplitude speed relation. Okay, so the amplitude and the speed here are related. And then back here, it's vanishing waves. And so that's an envelope of waves. It's a group velocity. And so we have a certain wave number that goes with that. Now I started with a jump, but all this information needs to come out from a theory that's going to describe what's happening here. Okay.
Sorry, when you say that this is unsteady, I mean, like everything's always propagating, but you mean that that in this case, kind of, it's like spreading, this pattern spreading. Whereas in the other case where you said it was a steady, then everything just propagates with that front and.
Yeah, you go in that reference frame and it's stationary. Yeah, it's steady. So here's a schematic of a DSW idealized. So we have all these oscillations. And if you zoom in to the middle, it looks locally like a periodic traveling wave. That's our modulated wave, right? And then we let it vary slowly over space and time, and we get the envelope structure. There's two distinct limits that are really important to call out. The zero wave number limit, that's the solitary wave limit, the leading edge, and a zero amplitude limit at the back, which is like the harmonic limit. Linear waves back there. Okay. So this wasn't proposed or discovered until Gurevich and Pitievsky solved the problem for KDB. And they did it in their original motivation was for collisionless plasma, actually. But it turns out this is probably more relevant for shallow water waves. And so, like I said, you have a jump, an initial jump, okay? You're giving an initial jump in the variable here, and you need to recover all that information. How are we going to do that? Well, we need to pose an appropriate initial value problem for the modulation system. Okay. And the way to do that is to require the jump in the mean to be characterized by this u minus u plus. In other words, the mean for x less than 0 is u minus, and for x greater than 0 is u plus. But that's only one relation that characterizes these three parameters, R1, R2, R3. So how are we going to get amplitude and wave number? Well, their key insight was to look for a self-similar solution known as a simple wave. And you only allow one of these Riemann invariants to change. And if you do that, then you're going to recover this full, what we call the DSW jump conditions and the DSW structure. So here's the structure. You can see the mean here is changing smoothly. And here's a picture again of what happens. And so from that dynamical systems perspective, what we're doing is we're actually using the entire family of periodic orbits all the way up to the edge, the homoclinic orbit of the solitary wave, or soliton in this case. And so rather than just a single guy, we're actually using this whole family. And we can characterize this jump condition. So namely the speed of the trailing edge and how it relates to the jump height, and the speed of the leading edge and how it relates to the jump height. We can also get the amplitude. And if you just take their result and you plot it on top of Favre's laboratory measurements, you don't do too bad. You don't do too bad. In particular, their key result is that the lead solitary wave or the lead oscillation should be twice the jump height. Okay, here it's not quite, but certainly the approximately linear amplitude growth here does seem to be reasonably well followed. Okay, and we could actually observe these in our experiment. You have to do a little more work to get those speeds. For example, the leading edge speed. But if you do that, the blue is the theory, and the crosshairs there are our measurements. So we don't do too bad. And then what about at the back? What about the trailing edge where the amplitude goes to 0? Well, the theory predicts that the speed could be negative if the jump is big enough. So let's take a really big jump and look at what happens. Okay, so we have to time things just so that it breaks at this spot. And sure enough, you see the envelope moving back. Even though the oscillations just keep expanding, that envelope's moving back. That's the negative speed. And this type of phenomena occurs all over the place, especially in geophysical scenarios. So internal atmospheric waves. You can't see this one well, but these are internal ocean waves. Ultra cold quantum gases, okay, so-called superfluids, so Bose-Einstein condensate. You can see it in magnetic spin waves, optics, quite a variety of scenarios where you can see this. Okay. Now, I want to give brief tastes of some more recent work. And I want to talk about multiple dimensions now. Okay, that was all 1D, and that's because it's nice for explaining and presenting. But you know, most of nature is there's multiple spatial dimensions. We live in 3D, right? So let's take this generalization of the KdV equation. It's known as the KP equation, and that just means you have shallow water waves with weak transverse variation. Okay, so that relates to your thing, but in shallow water. In shallow water, these waves are transversely stable. Okay, but in deeper water, they are unstable. So here, what we're going to do is do a simulation. I'm not going to go through the details, but it's periodic. I can explain more later. And this is a zoom in. But the idea is that we impart the 2D structure by putting a wedge. So U is 0 here, and it's 1 here, and there's a wedge with a certain slope initially. And so what's going to happen? Okay, we get some very interesting dynamics. So this one is for a relatively small slope. Okay, and we see up here and down here that DSW forming. Okay, if I went along here, it just looks like a 1D DSW, but it's slanted. But here we get this complex interaction and then the emergence of a very large amplitude oscillations in the middle. Run the other guy, and it's harder to see during the simulation, but here is a zoom in, right? So here we see the DSWs coming in at an angle, but here they're interfering. Okay, and we identify the bifurcation. So this is at a sharper angle. So we find a bifurcation in the interaction properties. So we call this Mach DSW reflection because it's related to Mach reflection of shock waves. Turns out that the process that is undergone here is very similar and can be related to the process of two oblique shock interactions. Okay. Namely, you get a triple point, and that triple point you can see right at the leading edge where you have this wave coming out and there's another wave going that way. Okay. Here we just have regular reflection. It's a nonlinear interaction, superposition. And very recently, there were some observations in a river in China, even just last fall. In fact, they were very excited. It's very nice drone footage. You can see movies of this, okay? They called it a new tide type. And I heard, translations from Chinese may not be ideal, but they called it a matrix tide or a fish scale tide. I don't know, you pick which one you like better. This one is very much analogous to our regular DSW reflection. You can see two bores that are just invading one another, and there's some interference pattern. This one shows a remnant of this kind of resonant type interaction. Now, the problem here is that this bore is undular, but this one has actually broken. The waves broke, and so we got whitewash. We got dissipation in the problem. So it's a little bit more complicated, but you do see that remnant of the resonance here. Okay. And you can compare with theory. I won't go into that, but that's where we would use our wave theory of waves to describe that process. So let me wrap up here with a nice application that is this is an animation of ocean currents and from a simulation. And we're interested in understanding how waves and mean flows interact. Okay. And this is very well studied in geophysical fluid dynamics. You can see, for example, this textbook. And let me try to bring it into the realm of within the spirit of what we've been talking about here. Okay. So there's a very interesting properties of the Whitham modulation equations. When I send the amplitude to 0, this is what they limit to. Okay. There's a mean, okay, and there's the linear waves being modulated. This is the same linear modulation equation I started with at the beginning of my talk, but now I have a mean, right, that drives the motion of the waves. The other natural limit to consider is the solitary wave limit or zero wave number limit. And again, we get a mean that's decoupled from the waves. In this case, it's solitons, but it's a soliton train now. Okay, it's a soliton train. And just like before, these admit a Riemann invariant structure, which you can use to your advantage. There's certain invariants that you can use. And so let me show you one example here. So this is an experiment in our lab where we create a broad disturbance. So rather than just create a bigger pipe and maintain it indefinitely, we brought it back down. So we're making a box. Okay? We made a box. And we let the box evolve. And what you see is it fission into a bunch of solitary waves. In this case, 14. Okay, that's the same as here. So this is a comparison of the experiment and a simulation of that equation I showed you. It's pretty dead on. And due to the structure of those modulation equations, one thing that you can immediately predict is the number of waves from your initial box. Okay. And this straight line is comparing asymptotic prediction of the number of waves with the actual observed number of waves. You can see we're within one or two for the whole range of experiments that we did. If you do a little further analysis, it's a little bit more tricky. You can actually predict the amplitude distribution. So I take each of these and I look at the amplitudes and I get a distribution. I normalize it. This is a cumulative distribution function. And the measured guy is the staircase. Because that's the measured. Each time I measure an amplitude, measure a guy, I get a stair up. And the curve is the theory prediction. That's pretty darn good too. Okay. So this modulation theory allows you to do quite a bit. Here's another fun one where now we take our DSWs and we interact solitons. We have to do that, right? It's just too tempting. Okay. And so we see a very interesting set of scenarios where either the soliton transmits or it gets stuck inside, trapping. And again, we can make some measurements. I'm not going to go into details here because I want to wrap up, but I want to show the last thing, which I think will be of interest. So the KdV equation here, and we go back to our spectral problem. And if we just had an individual soliton, this would be the solution, okay, with lambda I is written this way in terms of this parameter eta. Okay. And two of them experience a phase shift. The formula is given here. Okay, this is the phase shift formula. Now pose the following questions. Suppose I give a random distribution of solitons initially. Okay. And I ask, how do they evolve? Well, you can derive by generalizations of the wave theory of waves that I've told you about, a coupled system, a kinetic theory, if you will, for solitons. This is a kind of tracer speed of a soliton moving through a soliton gas with density of states or kind of soliton amplitude distribution F that satisfies this continuity equation. Okay. And you can see here an experiment where we just started pumping in a bunch of random pulses, and we get a very complicated mess here. And so a natural question is, can we try to understand this further? And one thing that we're working on right now, and I'm going to end with this, is to combine what we've been doing in the coherent or deterministic case with stochastics. In particular, suppose we now allow for the mean to change slowly in space and time, and then we have random solitons going through it. The mean can be just a rarefaction wave, so we have a step up, or a dispersive shock wave, we have a step down. Okay. And these are the spectral pictures for each of these scenarios. Okay. F is the distribution of solitons. and the lambdas describe the modulation of the mean. And it turns out, let me run some simulations here to see what happens. So you can see what we're depicting. The red is the back action that the solitons have on the rarefaction wave. They no longer decouple. You remember when I showed you the mean and the soliton, there was a decoupling. Now they're not, they're coupled. And we can do a similar simulation for the DSW. You see a remnant of it, but you saw that certain class of solitons got through. I didn't tell you, but the initial condition for these, these are what we call two-component gases. Okay, there's predominantly two amplitude components here. Okay, their positions are random, and so we get this nice process happening here. So I guess I'll conclude and just say I've gone through a kind of a wave theory of waves, little tour of kinds of work that's been going on in nonlinear dispersive waves. And the waves are traveling waves of nonlinear dispersive PDE, and the modulations are the Whitham equations, a quasi-linear first order system that also have wave type solutions. Okay. And applications, dispersive shock waves, and we talked about multidimensional effects. So this generalizes to higher dimensions. And then wave mean flow, I briefly commented on some interesting features there. Okay. So I think I'll conclude. I think it's Mardi Gras today, if I'm not mistaken. So anyway, thank you. Just want to put up a little advocacy. I saw you had signs around for this on Friday. So I'm going to the one in Denver. See you guys have one nearby too.
Just a naive question. I don't know much about waves, but when you form the solitons, are they all traveling with the same speed and they're evenly spaced?
No, they're not. Although in this case,
Oh, no, the experiment where you
the
had the I forgot where it was it before. No, not the gas,
one?
just the
You want the DSW. Got it.
yeah.
Here.
This one.
Oh, gotta keep it going. So you see this one's the fastest,
Yeah.
and more oscillations come out of the back.
Yeah. And
So
eventually,
they're all moving with different speeds.
yeah, and eventually you were saying that you were getting the soliton edge starts forming, solitons. So you had like 9, 10, whatever.
Ah, yeah, right. So this case, you can see that this diameter and this diameter are different. Let's compare that to this other scenario. Let me just go like this. Oops.
I should have remembered the number of the slide. Oh, yeah, that's the one.
Here, the difference is that this diameter and this diameter are the same.
Okay, so you turn it on and off. And so now all these solitons that you form, 6, 7, 8, are they all traveling with the same speed? Oh,
They satisfy the speed amplitude relation. So that's their nonlinear structure, right? So because they're nonlinear, their speed depends on their amplitude. Yep. So bigger ones in this case move faster than the smaller ones. That's right. So they separate. This is called the soliton resolution conjecture, which says that if I have a nonlinear dispersive PDE, I give some localized initial condition, let it run for a long time, I expect to see rank ordered solitons and radiation going the other way. And this is kind of a realization of that in an experiment.
thank you.
So you mentioned that with real systems, we have diffusion and this can cause waves to break.
Well, nonlinearity causes the waves to break, actually. But when they break, diffusion starts to matter, right? Because you're getting all this mixing, like whitewash.
Right. So I guess my question is there some sort of like bifurcation when there's enough diffusion that those like instabilities are possible? Or is it just the moment there's any diffusion at all that these waves are susceptible to this type of
So let me show you. So when does diffusion matter? That's your question.
Yes.
So we can quantify that. Okay. And so here we have diffusion and here we have dispersion. And we have parameters so we can look at the competition between the two. So here I'm showing you at a certain time, the scenario, this black one here, is when nu over epsilon is 0.05. Okay. But to get here, there was some evolution, right? So I had to let it evolve to get there. And so some dynamical process is leading to these development of these oscillations that eventually become steady. So if you make this really small, that time scale gets longer and longer, and it begins to look more like this on short enough time scales. So you can actually see the, let's say, dissipation-free dynamics for some period of time until the time scale at which this really kicks in. And then you'll get, it'll start to kind of amplitudinal decay, it'll start to relax to this.
So I'm just curious, so you talk mostly or a lot about the KdV equation. So how much is what you describe relying on being integrable? Because it seems like when you talk about these heteroclinic orbits and all these periodic, that actually has nothing to do with integrability as far as I can tell.
Exactly. Thank you for making that point. And I should have made that point, that this wave theory of waves is applicable as long as you have a family of periodic traveling waves that limit to zero amplitude and solitary wave. That's all you need, and enough conserved quantities to get the modulation equations. That's right. So, for example, this conduit equation is not integrable, not known to be integrable, and we could still get some analytical understanding from this modulation theory.
Can you see what kind of phenomena change?
Yes. So I didn't go into this, but kind of right now, there's a lot of work on, let's say, convexity. So the Whitham modulation system, in general, let me show it, kind of the general case here, just say the 3x3. Okay, we have this 3x3 system. And hyperbolicity is a necessity if you want to describe stable dynamics. Okay, that makes sense. But there's a more subtle understanding here that was recognized. This is boiling down to the theory of conservation laws. Okay, and in conservation law theory, there's another concept known as genuine nonlinearity. Okay, and that relates basically. That's the easiest way to say it. So let's just take a simple nonlinear wave equation like this. Okay. So the theory, the classical theory of shock waves says, as long as f double prime of u does not equal 0, then all the classical theory of shock waves apply. Jump conditions, entropy conditions, you can prove weak solutions, existence of weak solutions, and so on. But as soon as you get an inflection point here, then this system has different behavior. And that the generalization of that is to look at the eigenvalues and their relation to eigenvectors. Okay, in particular, integral curves are when I integrate in the direction of an eigenvector. And if the wave speed is not monotone, then I get this kind of generalization of this property where I lose, it goes through 0, and you can get all kinds of interesting things. Yeah. So very much, and our conjecture is that non-integrable systems are all non-convex. Okay, and that you need integrability to have convexity. All the examples we know of non-integrable systems, it appears to be non-convex.
Yeah, I think that's all that we have time for. So let's thank Mark.